Let us take a look at our first example. We have charge which is placed right at the center Q, surrounded by a conducting shell of radius A and B. These are spherical shells. And the first question is asking you what is the charge density at R is equal to A and R is equal to B. If we look at it, this question is basically a charge inside a cavity. And as we have seen in the notes, there must be a negative charge which is going to be induced on this inner surface, and the value of the negative charge must be minus q. And that has to happen so that if I make a Gaussian surface inside the conductor and I calculate the flux on the Gaussian surface, electric field inside the conductor is zero. So we are doing an integral of 0 should be 0, which tells you Q net should be 0 also. So the only way that can happen is if this charge, which I'm assuming, which is Q, is attracting a charge minus Q to the inside surface. Where is this charge coming from? This charge is migrating from the outside surface. And in migrating from the outside surface, it would leave a positive Q charge on the outside surface. The charge on the inside surface, this distribution would depend upon how this Q is placed within that cavity. And in this specific case, the charge which is present in the cavity is placed symmetrically around that surface. So everywhere I should have the same charge density because the problem looks the same to me from every single point on the surface, and thus the charge density should be uniform on the surface, and this minus q charge should be uniformly distributed over the surface area 4 pi a square. The charge which is distributed, the distribution on the inside part of the cavity depends upon how this charge looks with respect to that surface. The charge on the outside surface depends only on the shape of the outside surface. This density will only depend upon the shape of the outside surface. Remember what has happened when I brought this charge Q and it induced a charge of minus Q on the surface. Electric field here is equal to 0. The charge which is sitting outside is not seeing any forces due to these two charges. They have combined together to make the electric field 0 within the conductor, and thus that charge doesn't feel any more force from the charges which are sitting inside, and that charge would just distribute depending upon what the shape of the outside surface is, no matter what is happening inside. And thus, in this specific case, the shape which we have is a nice symmetrical sphere, and again because the shape is nice and symmetrical, the charge has to be symmetrical too. So the charge density again would be a constant and be given simply by the total charge Q spread over a surface area of a sphere with radius b, which would be q by 4 pi b square. So what we get is a charge inside a cavity which induces a charge minus q with a uniform surface charge and density and a charge plus q on the outside surface with uniform density of 4 pi b square. The next question asks to calculate electric field for different regions of R. I want to see how electric field and electric potential varies as I go to different points. So let's say we go to different points. We want to be able to define what the electric field and the potential there is going to be. Since we have to calculate these terms, and as we have discussed in class for both electric field calculations and electric potential calculations, the first question we always ask is the charge in the problem is symmetrical, and if it is symmetrical, can I somehow use Gauss law to calculate the electric field? Because if I can use Gauss law to calculate the electric field, I would first calculate with the electric field and then I will calculate the potential from that electric field. And in this case, yes, the answer is an obvious yes. Everywhere I go, I make a Gaussian surface, which is a spherical surface. Everywhere I go in any of these spherical surfaces, my charge, total charge, looks exactly the same, looks symmetrical, and thus I should be able to use Gauss law to calculate electric field. The next thing now we have to decide is how many regions we have. And you can see we have a region here which goes from 0 to A. Then we have a region inside which goes from A to B, and a region outside which goes from B to infinity. So we have region 1 which is bounded between 0 and A. We have another region where the conductor is present which is bounded between A and B, and the third region which is the outside part which is R greater than B. So we have to calculate electric field and a potential in each of these regions as a function of R. The values may be different in each of these regions, so we'll have to evaluate it out. And as we said in electric potential class, what do we have to do this? To calculate this potential, we have to go on a path, start from infinity, go on a path till we reach the point we want. And thus, in any such calculations, we always go outside in. So we will first look at the outermost region, then we will walk to the second region, and finally we will walk to the last region. Any time you have been asked to calculate potential and you want to use Gauss law, you always go outside in, which we have seen in potential class too. But if you have not understood it there, hopefully this would further clarify it out. So let's start with the outsidemost region. We'll calculate the electric field there, we will calculate the potential, and then we will start walking in. So I go to some point P here, which is a radius r away, a variable, and at that place I make a Gaussian sphere. There would be electric field E. Let's call it 3 to remind us it's region 3. So we are when r is greater than b. And if we apply Gauss law, all we get is E3 4 pi r square is the total net charge divided by epsilon naught. And in case you have conductors, what do we have? We have plus q minus q, and we have a plus q here. In conductors, when you have conductors present, when you go to the outermost region, the net charge is always and always going to be the charge which is present on the outside surface. You can convince yourselves q minus q, this q from the center, this minus q on that surface, plus q on the outside surface, that simply becomes q by epsilon naught, and thus my electric field is q by 4 pi epsilon naught r square. And if we want to put the vector is coming from inspection, is simply going to be r hat. So now we want to calculate the potential at that point P right here. What do we have to do? We have to go and choose a path, start from infinity, choose a path and calculate the work done at any specific place and integrate that. And we have seen that this integral is simply going to be minus infinity to r E3 dr, and thus V3 is going to be minus infinity to r q by 4 pi epsilon naught dr by r square, which is q by 4 pi epsilon naught r. We have not gotten any surprising results. The same observations we have been making before, that outside a symmetric sphere, it acts like a point charge, as if the whole charge was sitting in the center. Even when we have conductors, we get exactly the same thing. The electric field behaves as if whatever charge was present on this outside surface, in this case plus q, all that charge is sitting right in the center. That's, that is what the electric field is going to look like. And related to that, the potential is also going to look like a point charge. So now we have calculated the electric field in region 3. And in region 3, where we said we were outside the sphere, the electric field is simply that of a point charge sitting at the center, and the potential at any point r is also that of a point charge. Once I knew that the electric field was that of a point charge, I could have written this without even doing a full integral. Now let's come to region 2, always outside in. So I want to go to the region at a point P here. Again, electric field inside this has to be 0. It is a conductor, but is a potential 0. We have to remember, to reach at this point, we had to travel all the way from infinity first up to this region, and then across the region from there to there. So if we were going to calculate the potential at R, we have to first travel from infinity to B. So we have to first traverse this path, and in this path the electric field has the function of E3. So we have to do an integral of E3 dr, and then plus we have to take the extra step. This negative is coming because it is part of the definition of the potential. We have to go from B to R, E to R dr. E to R is simply 0. So when we travel from the edge to this point, we don't gain any potential. We remain on a flat curve, and thus, and the integral over here, we have already evaluated when I did the calculation for region 3. That integral is simply the value of the potential we saw in region 3 when R was equal to B, when we came to the boundary of that region, and simply KQ by B. Anywhere I go inside this conductor, the potential is going to remain the same, whether the point is here inside some volume or on the inner surface. Anywhere I go here, the potential is going to be KQ by B. And the electric field is going to be 0 because we are inside a conductor. So that is the result we're going to get when we are in region 2. Let's go to the next region, inside, outside, in. So now we come to region 1. And again, remember, we have found that in region 2, the potential is simply KQ by B for every point in that region. Now I want to come to region 1, and I want to calculate what the electric field and a potential there is. Electric field is straightforward. We can calculate that using Gauss law on this closed surface. We can basically write E1 4 pi r square is Q enclosed, which is simply Q divided by epsilon naught, and thus E1 is Q by 4 pi epsilon naught r square. To calculate potential again, we have to take a path all the way from infinity and see how high we climb as we get to this point. And that's why outside it helps us. Why? Because when we calculated the potential in region 2, we already know how much things have changed up to this point. Right at this place, we have already calculated that value. That value at the potential which we have on that edge is simply V2 at R is equal to A. V2 does not depend upon the position of R. That is a constant, so it would simply be KQ by B. And thus, my potential in one would be V2 at R is equal to A. I have reached this point. Now I have to go this extra step. So it would be plus minus. This minus again is in the definition of potential. We go from A to any point R and we integrate the electric field we are seeing there. Electric field is E1 dr. So that becomes KQ by B minus A to R KQ R square dr. I just substituted this value of E1 and just wrote it as KQ by R square. And we basically get KQ by B plus KQ by R minus KQ by A. So at any point, at any radius r away, the potential would be due to the point charge sitting there, plus the potential due to the sphere, which is KQ by B, and the potential due to the other sphere, which is minus KQ by A, because there's negative charge which is present there. Let's plot these functions and see what it looks like, what they look like. So I have electric field. Let's plot electric field first. We have a boundary A and a boundary B. Electric field inside is like a point charge, and let's say this line which I have done is that of KQ by R square, is like a point charge up to point A, and at that place it drops down to 0. Electric field in this conductor is 0, and then it starts following the same line again. So R and E. Right? If this conductor was not present, electric field magnitude would have remained on that same line if that conductor was not there. But because of the presence of that conductor, the field in that region between A to B has gone to 0, whereas the field outside is still behaving like a point charge. The field inside is still behaving like the same point charge sitting at the center. How does the potential look like? We have R, and again, let me draw a function which is of the form KQ by R. Outside B, the potential just follows. So remember again, V3 was KQ by R. Potential simply follows the original line of a point charge. Then between A to B, in that region, the potential does not change. It has a value of KQ by B here. Potential remains constant. You are going on a flat surface, and thus the potential at this place would be still KQ by B. What has happened is that if this conductor was not present, the potential would have been kq by A. But when you put the conductor, the potential has decreased to kq by B. With respect to kq by R, there has been a decrease of this value. Once I go to my region where R is less than A, I am still fighting the same electric field due to a point charge here. So what I should get, I'm still fighting the same. My electric field remains the same as if it was a point charge. However, instead of starting at this point and creating potential from that point, we have dropped down and we have created the potential is going to start from that place, and then it should follow the same curve as KQ by R curve. And these two curves should be parallel to each other. So if I go to any specific place, this point, let's say I've gone to a distance r, this point is kq by r. With respect to kq by r, I have dropped by that amount. What is that amount? It is kq by r minus this distance, which would be kq by A minus kq by B. Right? If this conductor was not present, the potential would have been kq by A. But now, because the conductor is present, the potential has dropped to kq by B. Again, remember A is less than B, so this term is greater than that term. And after I reach region 1, I have the same electric field as a point charge. Thus, my line or my potential variation should be parallel to what I observed before, and my potential in region 1 should simply be the parallel kq by r shifted below by so much distance. And let's see whether that is exactly what we saw before. Right? If you go back and look at the video before, this is the exact same expression which we saw. I could have written V1 without doing any integrals, just doing these drawings. There is another way we could have written V1, and that is with superposition without doing any integrals. Again, I have, and this will only work for spherical shells. I want to write a V1 here without doing any integrals. What I can do is I can see that this problem consists of a charge q, distance r away, plus a problem of charge minus q, and I want to go to a point r away, plus a problem of charge plus q sitting at B, and I want to go some r away. We can break this problem into some of these two problems. The potential are due to the first one, and this is basically now I'm using the thinking of k dq by r. Potential due to the point charge is simply kq by r. This is a spherical shell. with symmetric charge. And as we have seen before, potential inside a spherical shell, V at any r is simply V at the radius of that shell. Whatever is the potential I see in the radius is the same potential I get at the center, because there is no electric field. For this specific problem, there is no electric field. For this specific problem, there is no electric field. So the potential in the center is similarly is simple as potential on the surface, and potential on the surface is as if whatever is the charge sitting on the surface is sitting at the center. So the potential due to that would be the charge minus q sitting on the surface acting like a point charge sitting on the center, creating a potential of minus k minus q by a on the surface, which is the same potential at r. And similarly, the potential due to the second surface would be kq plus q. Now it is your capital R is equal to B. So I could have written this potential by looking at summation of these shells. What I would suggest you to do is use the integrals in the beginning till you get comfortable enough and can start seeing these things. And once you get comfortable enough, you should be able to write these potential terms, especially for spherical shells, without doing any complex integrals. This is our first example in the conductors chapter.